Hi, I'm Michelle Poland. I've nominated John MacLellan for the Varkey Foundation Global Teacher Prize. I've been a biology and chemistry teacher for 31 years. I've taught in 3 different cities in the area of Canada in which I live. I've taught internationally in Italy, and I've observed teachers at international schools in Brussels, Belgium. John is an exemplary teacher. He is the best teacher I've observed and had a chance to work with in my 31-year career. One of the criteria for the Global Teacher Prize is innovative and effective instructional practices. You're about to see a video where John demonstrates a model that he's developed that truly transforms how biology can be taught.
Mr. MacLellan?
Yes.
You came up with the model in 2005.
I did.
And that's been 12 years.
It's been a while.
Yeah. Could you tell us a little bit about how you came up with the model?
I would love to. On a Saturday, I came in and kind of designed a model very similar to this right now, where I could put O and manipulate it, because I would put a magnet on the back, and I would build an H and another H, put magnets. Now I had the ability to show what was going on at the level of the atoms. So this picture here now, boom, boom, is a completely different experience that the students would have of the history. Like anything is history, we can back up the timeline, pull them apart, and go, look, here's what it looked like before. So when I taught the very first lesson, which was 2 days later, one other idea I had in my head was my father, who was a very talented man and a huge influence on me, and I apologize, but these are photographs of some of his coal mining paintings that he did. So as a young boy, I would watch him in the basement paint these amazing pictures, and they would, the image would unfold gradually over time. So my idea when I come into class was, okay students, I am going to work just like my father did on a blank canvas. So my blank canvas is the blackboard. The students, for the first time in my teaching career at that point, weren't given any handouts. So I said, take out a sheet of paper, that's your blank canvas. And the instructions were simple. Follow me on the board and take your own note. They had to become responsible for the note. One of the directions I gave them, which we still use today, was I said, okay, look, here's a picture of what we're going to call before water, right? This would be before water. It's the history of water. So they would build on paper just what I have on the board. Then I said, okay, the next thing you're going to do is you're going to change before to during. So that is the motion. And in their note, they would show motion with arrows. And in this during picture, they would communicate why these 3 atoms are going to join together. The heart of their notes are really these during pictures. And then when the image is finished, they would have another picture called an after picture. So one thing that transformed me and my students immediately was this pattern of making before, during, right, and after diagrams, explaining in words what's going on, and now the students can see what I have in my brain as a history of what occurred and why it occurred. This image that my hand is on is a completely different experience to the student than this static, linear, no history to the story way of communicating what's going on. So when I taught that very first lesson on the Monday, which is still resonating with me 12 years later, It was a transformational experience. One of my students waited for me outside that door for 15 minutes to just tell me what an amazing lesson it was, which blew me away and also highly motivated me and touched me at the same time. So I could not explain to myself or anyone that I talked to, and I talked to thousands of different people in the last 12 years, about how I felt on that first day and how I feel when I teach. But recently what I've learned, I've read some very interesting research on brain biology. So brain cells are called neurons. So there are these neuron pathways that we have in our brain called mirror, like when you look in a mirror and you're brushing your teeth. These are called mirror neurons. So for example, when I drink water, as I just did, there are brain cells that light up because I'm drinking. When someone's watching me, their same brain cells, the same pathway lights up. So mirror neurons, one person who's doing something physical, the person who's watching is experiencing the same event. And that made so much sense to me. There's research done now in education on mirror neurons and how a physical manipulation can stimulate thinking. The students can predict. The students can mimic. So when we look at our stations here, here's where students would go and predict what could happen. They can mimic what happened. And that all leads to learning. Do you remember?
Hydrolysis.
Hydrolysis. What is a big clue? Put that kind of language wherever. Okay.
And then the phosphate dissociate off the ATP,
Right.
and it's going to bond to the OH.
Good. And do you remember what happens to that hydrogen?
It goes on to the ADP.
Okay, excellent.
And then this will go up here, up top, and the hydrogen will dissociate, and it will bond and make a water there, and then the phosphate will bond with it.
Okay, fantastic. Right? What's the name of this molecule now? It's not glucose anymore? Yes?
Glucose 6-phosphate.
Glucose 6-phosphates.
I have another question for you.
All right.
Could you tell us how your model works and what all these amazing colors represent?
Sure. In short, I would say that the model is one that can expand and contract, and in that way it's what I call multi-layered. There's different layers to it, and I'm going to do my best to demonstrate those now. So here's a classic image of what most people would see as like an atom. So what I did is I just took black magnets, I colored them. So that's a proton. That's a part of an atom. So it's a subatomic particle, and it's in the nucleus. I then took a black magnet and I painted it red. And electrons are smaller than protons, and they move in an orbit around the proton. So this would be one layer of the model. Now, this atom, one proton, one electron, is hydrogen. So now I can make a simpler model of what this represents. I continued to do that, so I could go 1, 2, 3 parts that are yellow, and those are called protons. And then you could go 2 electrons, and then 1, 2, 3, 4 electrons in this second shell. And this simplified version is carbon. So this is what I mean by expand. Here's an expansion of the model, and we can shrink it to this image, or we can shrink it to this. Now, most people know that carbon, climate change, carbon dioxide, hydrogen, oxygen, and nitrogen. Those are 4 key atoms in life. One of the things I love in life is music, and I'm a Beatles fan, as in the band The Beatles. You know, in the music that the Beatles play and other groups that play what I would call rock and roll, they can use like a guitar, a drum, a bass, and a piano and create magical songs using the same instruments. And this is exactly what life did. Life used the same atoms and arranged them like the Beatles did, or the Rolling Stones, or all songwriters. They arrange these notes and use these instruments to create new sounds. So one of the things the students would watch me do with them is what I call build a molecule. So we're using nitrogen, carbon, and carbon, and they would just see me do this. And we go. But I just wanted to give you one example of what I call an experience. So here's subatomic particles. We can make a simpler model here, here, and here, and we can use these simpler models now to piece them together and make a molecule. Now, this molecule has language to it. This is called it's a type of amino acid, and it has a name, serine, and its abbreviation is SIR. Now, what I've come to learn that's occurring, that I experience all the time, is that what I just built here in this picture, what I call atom by atom, the students experience that. What I am mimicking is how we learned as children. And what I've thought about is when a child learns the word tree, so the child experienced the real tree first. Once a child saw that tree, was curious about it, was most likely his parents then taught him the word tree. So in my understanding, experiences come first. We experienced what love was way, way before we could even speak, and then we put a word to it. So that's what's in my brain, experience, then language. Students are massively confused because we're giving them language with no experience. So no experience means that these cells are microscopic, they're invisible to the students, and here's language. So what I did is I built the experience. Here's an example of building the experience, naming the experience, classifying the experience. Now, here's another example of how the model can shrink. So I take this chemistry and I color it yellow, and the amino acid now is a circle that's yellow. Yellow means SIR. So one other connection that I've created with the model is a permanent. So this chemistry matches this chemistry. The students experience this atom by atom. Then I rebuild it and I laminate it, and I call this a magnetic memory. And if you just scan up here, Cecina, you can see all of these molecules are what we have studied already in this. There was a lesson I taught called the Ancient Sea.
Right.
They're all laminated and they're permanent magnetic memories. So the purpose is for us to practice and review and connect those molecules to the new lessons, the new stories that are being taught.
Okay.
There are 20 different amino acids. So I color coded them all, and I made a whole chain here of all these different colored circles. Each color represents a different amino acid. And then in biology, the power of this is that these amino acids bond together and then take on these magical, and they are magical, transformational shapes. This is kind of like a caterpillar transforming into a butterfly at the molecular level. Now we have a three-dimensional shape. So here's how the model expands. This model, I said, was layered. This image can expand to this image, but now you can take amino acids and expand them here. Now I can contract this protein like this. And the magic of biology, the magic of life, is the shape of these proteins. They're driving all the reactions in life.
Protein channels.
Worker protein.
5 worker proteins.
Protein channels.
Okay, so here's a new protein that I just built. And I'm going to wrap it around my hand in this very cool three-dimensional way. And I took this new protein I built, new idea, and what you're looking at here is the hand protein. So the students can see that this protein has a shape. The idea of the hand, they know that the hands can, do all these manipulations, which is what proteins do. And now I can take this here, this colored protein. So the hand protein is designed to connect to the color protein, to move the color protein close to the purple protein, and put the colored protein in the correct position so that, bam, magic. So now I'm going to show you a visual, a 3D visual of a mutation. So I'm going to show the hand protein is clearly changing shape. Let's call it the arm protein. So the hand protein is mutated to a different shape. That's a change. And in this mutated form, it can still attach to the multicolored protein and still move it, but only a little bit, up and down. And this multicolored protein is not going to connect to the purple because it's not in the correct position. So this could have a devastating effect for the cell. It could be some type of disease. And the students can clearly see a connection between the change in shape of a protein and how that can change a reaction. Bam. And what do we have here, Aurora? What's this?
My photosynthesis note showing the before, the during, and the after process. So when the sunlight enters the cell, the worker proteins are going to change shape. So I showed it by the tail coming to the bottom instead of the top. So for example, this carbon is going to be picked up by worker protein 1. The carbon dioxide is going to be split apart, so you have 6 O2s and just 6 carbons. The 6 carbons are going to be put into a carbon skeleton, which are going to, in the finished product, become glucose.
Okay, excellent. So can you just show me, because that was really good, can you show me the connection between these carbon here in the before picture and these carbon here by just putting your finger on one carbon in the before, and where would it be in the after?
This carbon comes and will travel through here, and it'll end up here.
Ah, okay. So it's the same carbon.
Yes.
And I like the way you said
change.
that. That's its trip, if you will.
Yes.
Okay, excellent. Okay. All right, ladies. What do we have? Are you working on this?
No, that's extra stuff. The picture
You're working on this?
Yes.
Okay, what am I looking at?
It's the before, during, and after pictures of the process of atoms bonding together, a non-metal and a metal.
Okay, so if I'm hearing you right, you said this is before?
Yeah. Mm-hmm.
This is your during picture?
Yes.
And this is after?
Mm-hmm.
Hi, I'm Sydney Clark.
And I'm Carolina. I'm behind the camera filming right now. And Mr. MacLellan taught us grade 9 science in the spring of 2017. And now that I'm in grade 10, I really miss being in his class because of all of the magnetic models that he has around. these that are hanging from the ceiling are my favorite. Coming in was super cool. So the models really helped to like understand the biology and chemistry behind all of his lessons.
It's really hard to pick a favorite one of Mr. MacLellan's lessons. All of his classes were so engaging and every lesson was so fun and very fascinating. If I had to pick a favorite though, it would definitely be the Ancient Sea, where we learned how the first cell formed 4 billion years ago.
So Sydney, can you show us how that actually happened, like with the models?
Well, this is just one part of the Ancient Sea where we learned how the first cell membrane formed, and this started with a phosphate molecule and 2 lipids, and they came together and formed a phospholipid.
Okay, so that's the bond, yeah.
Yes.
Okay, so what's that little green and yellow thing over there? What is that?
This is a mini version of this monster diagram.
Oh, I see that, like the little curve, yeah. Okay.
Yeah. And this happened because Mr. MacLellan decided to simplify it by taking the phosphate molecule and representing it with a green circle, and taking the lipid and representing it with these 2 lines.
All right, okay, cool. So, like, I see whatever that is over there.
Yes.
So, this is like the same thing, right?
Yeah.
Oh, okay.
Yeah.
All right,
This is a mini version of this, which shows a phospholipid bilayer. And if you take this and connect it with all of these, it represents a cell membrane.
All right, so that's just like the smaller version. That's so cool. All right. So that's your like favorite part.
Yeah, this is my favorite part of the Ancient Sea, which is my favorite lesson.
Awesome.
One other thing I'd like to talk about how the model can expand and contract, and how I try my best to get students to experience what's going on in the cell, is here's a major story we're studying, cellular respiration. I can manipulate this molecule like this with my hands and explain how this protein works. It's 2-dimensional. So that's 1 layer. Let's count them. 2 layers is, or I should say a second layer is, I can shrink all of this structure, laminate it. This is a magnetic memory. Here is the memory of what I just moved. So I'm going to go up to the board. So I'm going to place this memory on the blackboard to remind the students of what we studied, and to say, look, we're now going to examine this one part of the story. So I'm shrinking the model here, memory. Now I blow it back up. Here's what we have. I can show them the same reaction I showed at the back. So that was layer 1. This is layer 2. A third, what I call layer, is taking the molecule, the protein, right off the board. And now I can manipulate like this, and it's very 3-dimensional, but not quite as cool as this move, which would be a 4th layer. So this experience, the students can see the protein move, but my hands are not going to be involved in the bond. So the protein moves a bit, and then boom, magic.
As your former student for 3 years, I was wondering how you were able to create such a calm, peaceful, safe, and organized environment for your students.
Well, thank you so much for asking that. That's really at the heart of what I would say is the heart of how I teach. What I think about is creating a calm, safe environment. No one will convince me that students can learn in chaos. So I am consciously aware when I teach every moment that students need to be in a peaceful, safe environment, so they have the freedom to think, so they have the freedom to make mistakes, and they have the freedom to figure out how to figure out what they need to figure out, and that requires time, and it requires calmness. So how do I do that? That's a really interesting question. I do it because of how I prepare. And I prepare, and then when I finish preparing, I prepare again, and then I prepare. So what I've created here is, so for example, the sheet metal that I drilled into the walls all around the classroom. This is part of my preparation. Doing that physical work was, in my mind, like building a stage that a play would be conducted on. The stage is permanent, the stage is fixed. The sheet metal allowed me then to create lessons, and that to me is like a set. You know, Act 1 ends. When the curtain comes up for Act 2, there's a different set on the stage. The stage hasn't physically changed. So I create different images in my preparation. So here's a protein. You can see here, I think, it's in the shape of a letter Q, and this protein is called this protein is called Q. So building the stage, building the sets, and then when I deliver my lesson that I write in the stage with the sets, and that preparation then allows me to 100% focus on the students. So for example, in my preparation, right, if I just back up and I'm teaching my students like this, and I'm going to go to that meter stick that has Q on it, I'm not thinking about where it is. I'm not thinking about even what I'm going to do with it. I know where it is. I'm so well prepared. I can walk over here, pick this up, and start to move it. And if you notice how I'm turning, I'm now looking and focusing in on my students. They're seeing something new for the first time. I want to watch them watch what I'm doing, and this is how I can do it when I prepare this way. And I can guide them. They can ask me questions. I can then do physical movement around the room. I can look at this black circle and pull the students out of it and go over here and remind the students what that black circle represents. This is the chemistry of that black circle. I can ask the students to be reminded of a code. This is a genetic code for that black image. So, in conclusion, Cecina, the heart of what I do is an enormous amount of preparation. The joy that I get out of that is I actually love preparing, but I equally love when I deliver what I prepared. I have an incredible amount of freedom that connects me to my students. This goes back to the mirror neurons. I'm connected to the students because there's nothing interfering right now between me and my students. I'm here, they're there, and I've created what we both can communicate easily between. It's a common biology model, and that allows me to have peace, be at peace with myself, be calm, and focused on the lesson, but more importantly, them. And that's nothing but joy.
Awesome. Thanks, sir.
You're welcome. Is that a polymer?
Yes.
Is that different than a isomer?
Yes.
Can anyone explain what an isomer is? Yeah.
Molecules that have the same molecular chemical formula but different chemical structure.
Okay, good. And we're going to see that today. Now, we haven't gone over this much. Let's try it now, see what happens. This is a memory of what kind of reaction? Phosphorylation, right? So I'm holding, this was the worker protein. Remember serine? There's the OH. See the purple here? That would be the, what's that called? Kinases. Who can tell me what kinases do?
They conduct phosphorylation reactions.
They conduct phosphorylation reactions. We're going to see that today. Okay, let's do a spin. We're going in the back. Let's go. So this is a story that we're just starting to study. What's this called? Glycolysis. And it takes place, or the story of cellular respiration takes place outside the mitochondria, which you just identified as glycolysis. Most of it takes place inside the mitochondria. So what's the part that takes place here called? And here? And here? Glucose here, right? And so what I want you to visualize is that this molecule is hexokinase, okay? The whole thing. So I'm not gonna focus on that water reaction. So this is the one I was trying, remember the videotape we were trying to do? And it was okay, it wasn't as good as I thought, it wasn't as good as I wanted it to be. So all of this protein here and all of this is hexokinase. Do you remember that part in the enzyme where a molecule bonds to, the little pockets, what are they called? Active sites. So there's hexokinase active site for glucose. There's this active site for ATP. Now, the magic of biology, cell biology, is that this molecule places these two, look, you're watching, in the correct position here, not correct. Not correct, right? But when they're in the correct position, bam, okay? Now glucose gets phosphorylated. That happens because of the design of the enzyme, right? The power of mutations is if hexokinase gets mutated and has a different shape, the reaction doesn't occur. Sometimes that can be devastating and it could kill the cell. Sometimes it can be devastating and create a disease. Sometimes those mutations can be beneficial, right? But the key here is the position of these two molecules, okay? Glucose and ATP are controlled by that enzyme. In my world that I created for you here, if I place those magnets in the correct position, then the attraction occurs, okay? But that is exactly what's going on in the cell. It's not magnets that are attracting, right? It's electrons and protons, okay?
So, not exactly have the best. Then we just have to do it for this one.
Okay, now what? Like, what I'm doing, okay. So like we're taking alpha
There's only one oxygen.
6 glucose and we're phosphorylating it first and then we're taking the fructose and phosphorylating it.
So you're gonna add water, ATP. Yep. Yeah, exactly.
Can we go and get ATP from over there? Can we go get more ATP?
Yes, definitely. Hey girls, how's it going?
Good.
Okay, so what's the name of this molecule you think now?
So what are we trying to make?
Yeah.
Phosphorus.
So we got carbon what? Carbon, what number? 1. So it's fructose.
Another water?
Yeah. 1, 6, 5, the 5 being PI. Yeah, so it's fructose, 1, 6, 5, phosphate.
So it's all organic? Yes, it's organic. I know.
Yeah. So you want to say that? Fructose, 1, You make a mistake? Crack! Old school.
You have designed and built the first magnetic classroom.
Correct.
So what is your vision for the future?
My vision for the future is to then design and oversee the building of the first magnetic school in the world.
That sounds very interesting. So can you tell us a little bit more?
Sure. Well, the experience I've had in this classroom that I've been blessed to be in for the last 12 years has just led me to understand that if other classrooms and hallways and these specialized review rooms that I'll talk about later were available to students, it would just be another layer to help students learn. In this classroom, I've experienced this 360-degree view that I have of the cell and that the students have is a powerful view because we all are experiencing the history of the course without anything interfering with us. We're not turning pages or clicking computer screens. We have the story in the room and the story builds. So students have constantly told me that they really, really love being able to look and identify where molecules or stories are, review them, and then connect them to what we're now learning. And the other part that's really, really important, which is connected to being a former athlete, I'm not sure what I do today would be called athletic, but you know, any athlete, musician, actor, there's constant repetition. And the design of this room, without question, is tapping into my athletic background in creating a repetition of the material and repeat, and the students have an opportunity to do that visually just by sitting at their desks. So I think I'll show you a couple more ideas of this magnetic school in the hallway and in the library. Okay, here we are in our high school library, and you can see here we have a stack of books, and here we have a stack of books. So one of my visions is to make these kind of what I call panels. Just imagine these are all sheet metal. So the surface area here, each teacher can place what I would call a history of his or her course, and the students would walk through this maze that I would call a history of a particular course in a particular grade. These classrooms would be specifically designed for the students to continually to visit, to practice, and to remember what they were taught and how does it apply to what's going on today. I think of this environment that's in my head as a hybrid, as a mix between a museum and a library and maybe a classroom. We put up, Miss Webb and I put up this big piece of sheet metal last spring because my idea was to have a window display, you know, like in malls, you walk by the store and they're displaying, right, what's inside. It's like they want to attract you into the store. I was like, hey, if we put some sheet metal in the hallway, we can attract students, we can get attention, we can get students to think about biology or science. And this goes back to being up in the library. Imagine the hallway has sheet metal from floor to ceiling.
Right.
Look at the surface area where different teachers and different subjects could show again the history of their course or whatever they want to show. I think it's valuable real estate that we can easily tap into in a low-tech manner.